It is indeed a requirement to verify the conduit fill in fire alarm installations and confirm that the number of wires or cables does not exceed 40% of the conduit's volume. You must also apply the appropriate derating factor based on the number of conductors or cables present within the conduit. Let's delve into the specifics. Section 358.22 of the National Electrical Code, or NEC, places a limit on the number of conductors or cables allowed within a raceway, stipulating that it should not surpass 40% of the conduit's total fill capacity. The purpose of this limitation is twofold. Firstly, it ensures adequate space for heat dissipation from the conductors or cables. Secondly, it prevents potential damage to the insulation surrounding the conductors. Now let's turn our attention to derating. Section 300.15 (b)(2) of the NEC mandates the derating of conductors or cables housed within a raceway if the circuit itself carries a continuous load exceeding 10%. Derating is a critical safety measure implemented to prevent the conductors or cables from overheating. The derating factor applied is directly correlated to the number of conductors or cables present within the raceway. Fire alarm circuits typically fall under the category of non-power limited circuits, which are not subject to specific voltage or current limitations. Consequently, these circuits have the potential to carry a continuous load surpassing the 10% threshold. In such instances, the application of the derating factor becomes mandatory. Therefore, the approach to verify the conduit fill and subsequently apply the derating factor for fire alarm circuits is accurate and aligned with the code. Section 760.28 of the NEC explicitly states that fire alarm circuits must adhere to the requirements outlined in Article 300 of the NEC. This encompasses both conduit fill and derating regulations. Arguments against the necessity of checking conduit fill and applying derating factors for fire alarm circuits often stem from the misconception that these circuits operate at low amperage. However, it is crucial to recognize that fire alarm circuits can indeed carry a continuous load exceeding 10%, making derating imperative to prevent conductor or cable overheating. In conclusion, it is essential to verify the conduit fill and apply the appropriate derating factor for fire alarm circuits to ensure their safe and reliable installation. Now let us cover how to correctly calculate conduit fill and conductor derating to ensure compliance with the National Electrical Code. Firstly, we will discuss conduit fill calculations. To determine the allowable fill for electrical conduits, the NEC specifies percentage fill limitations based on the number of conductors within the conduit. For conduits containing 2 or fewer conductors, the maximum allowable fill is 40%. When there are 3 or more conductors, this limit reduces to 40%. These limitations apply to ensure adequate space for heat dissipation and to prevent mechanical damage to the conductors during installation and operation. To calculate the conduit fill, you need to know the inner diameter of the conduit and the outer diameter of each conductor. Here's a step-by-step guide. 1. Determine the conduit type and size you plan to use, such as ENT, PVC, or rigid metal conduit. Each conduit type has different inner diameter specifications, which can be found in NEC Chapter 9, Table 4, or from conduit manufacturer's data. 2. Identify the conductors you will be installing in the conduit. For each conductor, determine its outer diameter, including any insulation. This information is typically available from the conductor manufacturer. 3. Calculate the cross-sectional area of each conductor using the formula area equals pi times radius squared, where the radius is half of the outer diameter. Make sure to use consistent units, typically inches, for both diameter and area. 4. Sum the cross-sectional areas of all conductors to obtain the total conductor area. 5. Refer to NEC Chapter 9, Table 4, to find the inner diameter and corresponding cross-sectional area of the conduit you selected. 6. Calculate the allowable fill area by multiplying the conduit's cross-sectional area by the allowable fill percentage 40% for 3 or more conductors. 7. Compare the total conductor area to the allowable fill area. The total conductor area must not exceed the allowable fill area to comply with NEC regulations. If the total conductor area exceeds the allowable fill area, you must either increase the conduit size or reduce the number of conductors in the conduit. Now let us examine conductor derating for conduit installations. When multiple current-carrying conductors are installed in a conduit, the NEC requires that the ampacity of each conductor be derated to account for the reduced heat dissipation capability. This derating is necessary to prevent overheating of the conductors, which can lead to insulation damage and potential fire hazards. Here's how to apply conductor derating. 1. Determine the allowable ampacity of each conductor based on its size and insulation type. The allowable ampacity is the maximum current a conductor can carry continuously under specific conditions without exceeding its temperature rating. This information can be found in NEC Table 310.16. 2. Count the total number of current conductors in the conduit. According to NEC Article 310, a current carrying conductor is defined as a conductor that carries current continuously for 3 hours or more. Neutral conductors are generally not considered current carrying conductors unless they carry a significant amount of unbalanced load. 3. Refer to NEC Table 310.15. The 3a, which provides adjustment factors for conductor ampacity based on the number of current carrying conductors in a raceway or cable. The adjustment factors are expressed as percentages and are applied to the allowable ampacity of each conductor. 4. Multiply the allowable ampacity of each conductor by the appropriate adjustment factor from NEC Table 310.15. The 3. To determine the derated ampacity. For example, if you have 7 to 9 current carrying conductors in a conduit, the adjustment factor is 70%. If the allowable ampacity of a conductor is 30 amps, the derated ampacity would be 30 amps times 0.70, which equals 21 amps. 5. Ensure that the derated ampacity of each conductor is sufficient for the load it will carry. If the derated ampacity is not sufficient, you must either increase the conductor size, reduce the number of conductors in the conduit, or take other measures to reduce the load on the conductors. Here are some additional considerations to keep in mind when calculating conduit fill and conductor derating. Firstly, always refer to the latest edition of the NEC for the most up-to-date requirements and tables. Electrical codes and standards can change over time, so it's essential to stay informed of any revisions or updates. Secondly, consult with a qualified electrical engineer or inspector if you have any questions or concerns about conduit fill or conductor derating. They can provide valuable guidance and ensure that your electrical installations comply with all applicable regulations. Thirdly, consider the effects of ambient temperature on conductor ampacity. The allowable ampacity of conductors is typically based on an ambient temperature of 30 degrees Celsius or 86 degrees Fahrenheit. If the ambient temperature exceeds this value, you may need to apply additional derating factors as specified in NEC Table 310.15. B2. Fourthly, be aware of any local codes or regulations that may supplement or modify the NEC requirements. Some jurisdictions may have stricter rules regarding conduit fill or conductor derating, so it's essential to comply with all applicable codes and standards in your area. Fifthly, proper documentation is crucial for electrical installations. Keep detailed records of all conduit fill calculations, conductor derating, and other relevant information. This documentation can be helpful for future reference, maintenance, and inspections. Now, let's talk about some specific considerations for fire alarm circuits. Fire alarm circuits, while often low amperage, are critical for life safety. The NEC provides specific requirements for these circuits to ensure their reliability and functionality during emergencies. Firstly, power-limited and non-power limited fire alarm circuits are defined differently in the NEC and have different installation requirements. Power-limited fire alarm, or PLFA, circuits are subject to voltage and current limitations, while non-power limited fire alarm, or NPLFA, circuits are not. Secondly, fire alarm circuits must be installed in accordance with NEC Article 760, which covers the installation requirements for fire alarm systems. This article provides specific guidelines for wiring methods, conductor sizing, overcurrent protection, and other aspects of fire alarm circuit installations. Thirdly, fire alarm circuits must be electrically supervised to ensure their integrity. Electrical supervision involves monitoring the circuit for opens, shorts, and grounds, and providing an indication of any fault conditions. Supervision is typically achieved through the use of end-of-line resistors or other monitoring devices. Fourthly, fire alarm circuits must be protected against overcurrent. Overcurrent protection devices, such as fuses or circuit breakers, must be selected and installed in accordance with NEC requirements to protect the circuit conductors from overloads and short circuits. Fifthly, fire alarm circuits must be properly identified and labeled. Conductors and equipment associated with fire alarm circuits must be clearly marked to distinguish them from other electrical systems. This helps prevent accidental disconnection or interference with the fire alarm system. Sixthly, when calculating conduit fill and conductor derating for fire alarm circuits, it's essential to consider the specific characteristics of the circuit and the equipment it serves. For example, some fire alarm devices may have higher inrush currents or continuous loads than others, which can affect the conductor sizing and derating requirements. Seventhly, coordination with fire alarm system designers and installers is crucial. They can provide valuable insights into the specific requirements of the fire alarm system and help ensure that the electrical installation complies with all applicable codes and standards. Eighthly, regular testing and maintenance of fire alarm circuits are essential for ensuring their continued reliability. Testing should be performed in accordance with the manufacturer's recommendations and applicable codes and standards to verify the proper operation of the fire alarm system. Ninthly, documentation of fire alarm circuit installation should be thorough and accurate. Keep detailed records of all wiring diagrams, conductor sizing, overcurrent protection, and other relevant information. This documentation can be helpful for troubleshooting, maintenance, and future modifications to the fire alarm system. Now, let's address some common misconceptions regarding conduit fill and conductor derating. Firstly, one common misconception is that conduit fill limitations are only intended to prevent mechanical damage to conductors. While it's true that excessive conduit fill can make it difficult to pull conductors and potentially damage their insulation, the primary purpose of these limitations is to ensure adequate heat dissipation. Secondly, another misconception is that conductor derating is only necessary for high amperage circuits. However, even low amperage circuits can generate significant heat if multiple conductors are bundled together in a conduit. Conductor derating is essential for preventing overheating regardless of the circuit's amperage. Thirdly, some people believe that the NEC requirements for conduit fill and conductor derating are overly conservative and unnecessary. However, these requirements are based on years of research and experience and are designed to ensure the safety and reliability of electrical systems. It's always best to err on the side of caution and comply with the NEC requirements, even if they seem overly strict. Fourthly, a common misconception is that using larger conductors will eliminate the need for conductor derating. While it's true that larger conductors have higher ampacities, they are also more expensive and may not always be practical or necessary. Conductor derating is still required, even with larger conductors, to account for the reduced heat dissipation capability in a conduit. Fifthly, some people believe that using heat-resistant conductors, such as those with a 90 degrees Celsius temperature rating, will eliminate the need for conductor derating. While heat-resistant conductors can withstand higher temperatures, they still generate heat when carrying current. Conductor derating is required to ensure that the temperature of the conductors remains within their allowable limits. Now, let's discuss some practical tips for complying with conduit fill and conductor derating requirements. Firstly, plan your electrical installations carefully. Before starting any wiring work, take the time to plan the layout of your circuits and determine the number and size of conductors you will need. This will help you select the appropriate conduit size and minimize the need for conductor derating. Secondly, use the correct conduit size. Selecting the right conduit size is crucial for complying with conduit fill requirements. Refer to the NEC tables and calculations to determine the appropriate conduit size based on the number and size of conductors you will be installing. Thirdly, avoid overfilling conduits. It's always better to err on the side of caution and use a slightly larger conduit size than necessary. Overfilling conduits can make it difficult to pull conductors, increase the risk of insulation damage, and reduce heat dissipation. Fourthly, use cable pulling lubricants. When pulling conductors through conduits, use cable pulling lubricants to reduce friction and prevent damage to the insulation. Select a lubricant that is compatible with the conductor insulation and conduit material. Fifthly, properly support conduits. Conduits must be properly supported to prevent sagging and damage. Use conduit clamps, straps, or hangers to secure the conduits to walls, ceilings, or other structures. Sixthly, consider using cable trays or wireways. In some cases, it may be more practical to use cable trays or wireways instead of conduits. Cable trays and wireways provide more space for conductors and can make it easier to install and maintain electrical systems. Seventhly, use color-coded conductors. Color-coding conductors can help prevent wiring errors and make it easier to identify circuits. Use standard color codes for hot, neutral, and ground conductors. Eighthly, label all conduits and conductors. Labeling conduits and conductors can help prevent confusion and make it easier to troubleshoot electrical systems. Use permanent labels that are resistant to moisture and abrasion. Ninthly, inspect your work. After completing any wiring work, inspect your work to ensure that it complies with all applicable codes and standards. Check for proper conduit fill, conductor derating, and support. Finally, maintain documentation. Keep detailed records of all electrical installations, including wiring diagrams, conduit fill calculations, and conductor derating. This documentation can be helpful for future reference, maintenance, and inspections. Let's cover some examples of conduit fill and conductor derating calculations. Firstly, example 1. A 1-inch E&T conduit contains 3 number 12 AWGTHHN conductors. The conductors are carrying a continuous load of 20 amps. Is the conduit fill within the allowable limits, and do the conductors need to be derated? Solution from NEC Chapter 9, Table 4. A 1-inch E&T conduit has an inner area of 0.864 square inches. From NEC Chapter 9, Table 5a, a number 12 AWGTHHN conductor has a cross-sectional area of 0.133 square inches. The total conductor area is 3 times 0.133, which equals 0.399 square inches. The allowable fill area is 40% of 0.864, which equals 0.3456 square inches. Since the total conductor area 0.399 square inches is less than the allowable fill area 0.3456 square inches, the conduit fill is within the allowable limit. From NEC Table 310.15. The adjustment factor for 3 current carrying conductors in a conduit is 80%. The allowable ampacity of a number 12 AWGTHHN conductor is 30 amps. The derated ampacity is 30 amps times 0.80, which equals 24 amps. Since the derated ampacity 24 amps is greater than the continuous load 20 amps, the conductors do not need to be derated. Secondly, let's do example 2. A 3/4-inch PVC conduit contains 6 number 14 AWGTHHN conductors. The conductors are carrying a continuous load of 10 amps. Is the conduit fill within the allowable limits, and do the conductors need to be derated? Solution from NEC Chapter 9, Table 4. A 3/4-inch PVC conduit has an inner area of 0.533 square inches. From NEC Chapter 9, Table 5a. A number 14 AWGTHHN conductor has a cross-sectional area of 0.97 square inches. The total conductor area is 6 times 0.97, which equals 0.582 square inches. The allowable fill area is 40% of 0.533, which equals 0.2132 square inches. Since the total conductor area 0.582 square inches is less than the allowable fill area 0.2132 square inches, the conduit fill is within the allowable limits. From NEC Table 310.15. B3. A. The adjustment factor for 6 current carrying conductors in a conduit is 80%. The allowable ampacity of a number 14 AWGTHHN conductor is 20 amps. The derated ampacity is 20 amps times 0.80, which equals 16 amps. Since the derated ampacity 16 amps is greater than the continuous load 10 amps, the conductors do not need to be derated. Thirdly, let's look at example 3. A 1/2-inch rigid metal conduit contains 9 number 10 AWGTHHN conductors. The conductors are carrying a continuous load of 25 amps. Is the conduit fill within the allowable limits, and do the conductors need to be derated? Solution from NEC Chapter 9, Table 4. A 1/2-inch rigid metal conduit has an inner area of 1.50 square inches. From NEC Chapter 9, Table 5a, a number 10 AWGTHHN conductor has a cross-sectional area of 0.211 square inches. The total conductor area is 9 times 0.211, which equals 0.1899 square inches. The allowable fill area is 40% of 1.50, which equals 0.60 square inches. Since the total conductor area 0.1899 square inches is less than the allowable fill area 0.60 square inches, the conduit fill is within the allowable limits. From NEC Table 310.15. B3. A. The adjustment factor for 7 to 9 current carrying conductors in a conduit is 70%. The allowable ampacity of a number 10 AWGTHHN conductor is 35 amps. The derated ampacity is 35 amps times 0.70, which equals 24.5 amps. Since the derated ampacity 24.5 amps is less than the continuous load 25 amps, the conductors need to be upsized. To handle the 25 amp continuous load after derating, a conductor with an ampacity of at least 25 amps divided by 0.70, which equals 35.71 amps, is required. A number 8 AWGTHHN conductor with a allowable ampacity of 50 amps would be suitable. Upsizing the conductors ensures they can safely carry the continuous load after derating. These examples illustrate how to apply the NEC requirements for conduit fill and conductor derating in various situations. Always refer to the latest edition of the NEC and consult with a qualified electrical professional for specific applications. In conclusion, always prioritize safety and code compliance when working with electrical installations. Understanding and adhering to the NEC requirements for conduit fill and conductor derating is essential for preventing electrical hazards and ensuring the reliable operation of fire alarm circuits and other electrical systems.